wave functions and extract the momentum distribution function from the total wave function, and I show that this momentum distribution function can have universal shape. And at the end, I summarize my talk. The main goal of this study is to have a very accurate solution of the four-body bound state problem. Of course, for the weakly bound state, because the nature showed that this weakly bound state, the existence of the weakly bound state in different sectors of the physics, I mean that from the atomic physics to the nuclear physics. And we can see that this weakly bound system with large scattering lengths can have universal features which are independent of the interaction, I mean that the details of the interaction. So it would be interesting to study these universal features, and a real example for this weakly bound state can be seen in the ultra cold atom, and in the nuclear physics we can see this system with large scattering lengths in halonuclei. So for a study of this weakly bound state, different technique has been used, from the Noether-Scher model and hyperspherical harmonic, effective interaction hyperspherical harmonic, and also beside the other green function Monte Carlo, coupled rearrangement, channel Gaussian variational, stochastic variational, and Fedorov-Jakubowski formalism. That in this talk I mean that work in the Fedorov-Jakubowski formalism for studying these weakly bound systems. For those who don't have the background information about the FMO physics, I present this slide to give some idea about this FMO physics. The FMO scenario refers to a system of two particles where interact in such a way that the two body bound state is exactly on the verge of being formed. So adding the third particle to system can lead to an infinite number of the three-body system. And these systems are completely identical, except that the size and the binding energy are different and are connected together with a universal scale 22.7. That this is the ratio that we can see in this FMO three-body binding energy. This physics can be schematic, can be represented in this figure. That here we have the three-body binding energy as a function of the scattering, inverse of the scattering length for the negative scattering length, and here we have the positive scattering length. Here we see that one negative scattering length, a trimer merge the three-atom resonance, and by increasing the scattering length, the next trimer can appear, and by increasing to infinite scattering lengths, we can have infinite number of the trimers with the energy that scaled by the factor of 22.7. Of course, in the positive scattering lengths, we can have this atom dimer resonance. So it means that we can this trimer state, ground, fast excited, and so on, can disappear in this atom dimer resonance. Of course, we can have some information for this point. That when the trimer appear or disappears, that in which scattering length this can happen. So this physics observed for the first observation of this effect is reported in the paper by Kramer et al., and they have used the ultra cold gas of cesium atoms, and then this universal factor 22.7 that appears in the that predicted by FMO in 1970 is confined that about 40 years after that this theoretical prediction by different experimental groups. So the question is that if FMO three-body physics, what will happen if we add that one more particle to the system? Can we have the same scale for the the tetramers, or how many states we can have for each or associated with each trimer state? So based on this motivation, different theoretical study has been done with different groups. Can say that the Platter and Hammer have done some calculation, phase calculation for this Four-Boson system with large scattering lengths, and they have predicted two tetramer, weakly bound tetramer associated to each trimer. And also there are other calculations. These studies, they're done in effective field theory, and also the other calculation by hyperspherical harmony and other. We have also the Deltuva calculation in the AGS formalism. So we have also, beside this calculation, we have also studied this four-boson system, as I said, in the Fedorov-Jakubowski formalism. And here we see the abstract of the calculation of the, the other groups. For a three-body system, as I said, we have infinite number of the trimer state associated with this Efimov scale in the size and the energy. And the four-body calculation, for example, here we have the result by Stasher and al. That for each trimer we can have two tetramers with the binding energy ratios 1.01 for the excited trimer and 4.6 for the ground tetramer. That connected to each trimer. So the prediction by Hammer and Platter is for these binding energy ratios, the two tetramers is 5 and 1.01, and this is the recent Deltuva calculation, 4.61 and 1.00227, and also the Getto-Biggio calculation is they have predicted 4.5 and 1.020. So they have shown that by using just a two and three body interaction, we can have two tetramers associated with each trimer. So we tried to, that in an independent calculation by using a zero range interaction to see that we can, that how would be our prediction for this tetramer binding energy. Can we have just?
These numbers for the model in which error is zero,
this is the prediction for, that at the unitar limit, that when we increase the scattering lengths to go exactly at the unitar limit and to, that this is the, yes.
Elasticity is zero also.
Yeah, yeah, yeah.
So did people extend that calculation to a case where error is not zero?
Not that I know of.
So first I start the Fedorov-Jakubowski formalism for the four-body bound state. In the Jakubowski formalism, for the four identical mass particles, we can have two independent structures. We call them as 3+1 or call these as a K channel, and we, the another one can be 2+2 channel or this H channel. They are connected together as this coupled equation. Here G0 is free propagator, T12 is the two-body or transition of amplitude in the two-body subsystem 1, 2. P is permutation operator which acts in the three-body subsystem. P34 permutes the particle, and 3 and 4. The K is so I have a problem with pointer. Yeah. So we have also the K channel, and which is coupled to also to H, and here we have G0 free propagator, again transition amplitude, permutation operator which permutes the particle in the two-body subsystem 1, 2 with the particle in the two-body subsystem 3 and 4. And the total wave function of this four-body problem can be composed of 18 components. We have 12 component of K type, the 3+1, and 6 component of 2+2 that can compose together to, to give the total wave function of this four-body problem. So for representation of this coupled Jakubowski equation momentum space, we need to define the, the basis state. The basis state contains 3 Jacobi momentum vectors. In the 3+1 chain, we have U1, U2, and U3. U1 is the relative momentum of the particle in the two-body subsystem. U2 is the momentum of the third particle with respect to the central mass of the two-body subsystem, and U3 is the momentum of the fourth particle with respect of the central mass of the three-body subsystem. Here we have V1, V3, the relative momentum of the particle in the two-body subsystem, and V2 is the relative momentum of these two-body subsystem. So the projection of the Jakubowski component in the introduced basis state, I mean that the K projected in the basis corresponding to 3 plus 1 chain, and H is projected in the basis corresponding to 2 plus 2 chain. We see, I mean that here I have, I mean that presented in diagram to see that, for example, the transition amplitude T1 do X in the, I mean the subsystem with the same color, permutation operator P act in the three-body subsystem. Here we have, I mean that a completeness relation because we have the H component, so we need to have a corresponding basis state. So we need to evaluate some transformation between two different structure of this chain. So this can be evaluated by, I mean that considering the subsystem 1, 2 as a, I mean that one particle, and reduce these to a three-body problem and evaluate this transformation. We have, I mean that some transformation permutation operator gain for the H channel, and for calculation we are using a zero range interaction, and this zero range interaction can, the Lippmann-Schwinger equation can be solved for this transition amplitude in this form that the strength parameter lambda can be, I mean that obtained by using the pole property of the transition amplitude in the two-body or dimer binding energy. So we can have the analytical form of the transition amplitude for a given scattering length, of course for the zero range, which can be connected to the dimer binding energy for a given energy in this form. So at the end we can have the coupled Jakubowski integral equation as a function of two Jacobi momentum. I mean that we don't see the dependence of the first Jacobi momentum because of the, I mean that the simplification that we can do for a separable potential. So here we have transition amplitude that we can have, I mean that the analytical form. Here we see that we have defined some G0 with label 3, and in other term we have G0, 4, 4, 4, 4. This is the subtracted form of the Green function, which contains just a three-body parameter, and in other term which appears in the presence of the fourth particle, we have defined the subtracted Green function with the four-body regularization parameter. We can have a look to this figure, I mean that exactly corresponding to this equation. We have the K projected in 3 plus 1 and H projected in 2 plus 2 chains. So it is connected to K, K, H, and this 2 plus 2 is connected to 3 plus 1 as 2 plus 2 component. So the A term is exactly the term is, I mean, that corresponding to the three-body problem when we, I mean, that ignore the force particle. So for the solution of the Faddeev equation, for this case, we need a three-body regularization parameter to solve the Faddeev equation and to, I mean, the study system. In all other terms, that, I mean, that for other terms that appears in the presence, I mean, that by considering the addition of the force particle, we have introduced a new for body regularization or for body parameter, which is, I mean, that defined in this form. I mean, that this is the explicit form of the subtracted Green functions. The difference is that in this term corresponding that with the three-body, we use just a three-body regularization parameter, and in other term we are using a four-body parameter. So, yeah.
At this point, are you simply saying that there could be a four-body parameter, or have you already done a calculation that shows
This is the
that
challenge between, I mean, that our calculation and with other, I mean, that prediction. Numerically, if I want to say, if I use a same three and four-body parameters by using this zero-range interaction, numerically I can see just one tetramer. I mean that this is that I can, I mean that in continuation I show. So that's why if I think in other way, if I want to see that how we can how the same spectrum for the tetramer binding energy as predicted by other groups. So this is that we need to have these 4 body parameters. So this is the, the numerical, at least from this numerical point of view. I mean that I can show the result and we can discuss about that. So,
understand, where do you get this UN from which other condition? Is there an additional condition or is it a free parameter?
actually this 3 body, the parameter can be corresponding to the 3 body force that can be, that used to, to fit the physics of the 3 body parameter, that one observable and predict the other observable.
But is it clear how that corresponds to a three-body force? I mean, that it's some kind of cutoff in your equations.
Mm-hmm.
But how do you know it corresponds to a three-body force?
I cannot see a direct connection between this parameter and the 3 body force. But the point is that when we solve the Faddeev equation and we gain, that we obtain the FMO spectrum for this 3 body, physics, we can see that it leads to the same result as, that for example, you have used a contact interaction 3 body force in your spectrum to obtain the same picture. So that's why we say that it can be corresponding to a 3 body force or parameter.
But within your way of thinking about this, why do you introduce a 3-body parameter in the first place?
Mm-hmm. So we are using a zero-range interaction.
Right.
We need to solve the Faddeev equation. To regularize this integral, we need to solve, that a regularization.
At that point, you see that you have, if you don't introduce this parameter,
For
you
sure.
have a cutoff dependence over
Yeah,
your integral
sure.
over
Yeah,
them.
yeah.
But you are saying that for the 4-body, you don't follow the same strategy. You don't use the same argument to introduce this 4-body parameter. Is that what I understand?
No, that if I use the same 3-body parameter, that the same value of the 3-body parameter for the 4-body, I can see just one, the tetramer in my
Yeah,
spectrum.
your equations are well defined and so on. You are not
But for numerical solution, for sure, we need to have a, that regularization parameter for these other terms. Otherwise, that we have again the same problem that we had for the 3-body, that case to solve this integral equation.
But then I think I'm confused
Mm-hmm.
about your answer to my question.
Mm-hmm.
So if you say you don't put the 4-body parameter, then do you mean you put it to be equal to the 3-body
Yes,
parameter?
yes.
And then you only get one bounce?
Exactly,
in the
yeah,
4-body
yeah.
sector?
Yeah. So it doesn't mean that we don't need to this 4-body parameter. It can be interpreted in this way, that we have 2 parameters that are equal together, and okay, so it means that we don't have the 4-body parameter, so this is exactly the same parameter that we have used in the 3-body system. So it can lead just one tetramer in our calculation. So for the numerical solution of this coupled equation, so it can be written in this eigenvalue form. That we can have a vector composed of the component k and h, and this has eigenvalue equal to 1. This is the kernel, and so we solve this equation, eigenvalue equation, by iteration method. That we start the iteration by an arbitrary function. We apply the kernel, and we at the end we can see that that for after discretization of the momentum and angular variable, we can have a huge kernel, and it means that the direct diagonalization of this kernel is not possible. And another point is that for the mapping of the momentum variables, we should be careful, because the tetramer, some of the tetramer state, we can see that are, the main distribution of the wave function is concentrated in close to, that very low momentum. So it means that uncareful, that mapping of the momentum variable can be lead us to that we don't obtain or calculate this tetramer state. For the, to avoid this, the diagonalization of this huge matrix, we use the iterative orthogonal vectors method. That this is based on iteration.
Maybe
we
let me ask another question
yeah.
on your mesh points. Do
Yeah.
you distribute them linearly, or do you have some special?
We have a spatial mapping, hyperbolic mapping. I can show in my example. Yeah, this is very important because if I use the linear mapping, sometimes I cannot see some. I mean the tetramer states. So the idea of this Langevin technique is that we obtain a set of vector by the iteration method, and we can construct an orthonormal basis, and at the end, after for example 10 iteration, we can have 10 minus 1 vectors. The dimension of the matrix that we need to diagonalize is very small in comparison to the first the kernel that we had. So this is a very powerful method that is used in the nuclear calculation. We need also multidimensional interpolation during this iteration procedure on the the Jakubowski component. So we are using this cubic Hermite spline for using because of its high computational speed and accuracy. Here we have the result for tetramer ground and excited binding energy exactly at the unitary limit by using this zero range interaction. Here we see that the ratio of the 3 and 4 body regularization parameter, this is 1, and here we increase this ratio. As I said, if we have the same value of the scale ratio, we have just one ground state. When we increase this ratio, we see that in some point, when the ratio of the ground tetramer is about 4.6, more or less, we can see that the next, the tetramer appears. If we increase again the scale, we see that in some scale ratio, when the ratio between the first excited tetramer with respect to the ground trimer is 4.6, the next excited or second excited tetramer appears. So I mean that we see that these ratios are repeating here, and we see the same cycle behavior in the behavior of the binding energy ratios. So we can have that it's numerically so hard, but we that we approach this point that in this point we can have even more excited tetramers. But
the absolute value of mu3 is?
Here we fix the mu4 equal to 1, and we decrease the value of mu3, because numerically if I fix the mu3 and increase the value of the mu4, I see the convergence in the binding energy so that's
what I'm interested in is what is the relative size of mu3 squared and your ground state trimer?
Yeah. So for B2 equal to 0, we see that B3 is 2.7173 mu3 square. So this is for ground.
So you need all the digits.
Yeah. So because I have done the calculation for at the unitary limit for 5 trimers, so that's why that the precision is important for this calculation. Of course, we can.
The states that you calculate are attached to this trimer B30, right?
Yes, exactly.
So since the energy of that trimer state is certainly of the order factor of 10 larger even than your cutoff parameter. So it could be that the results you see here are just due to the fact that you are in the ultraviolet, and these are ultraviolet artifacts of your theory.
So you mean that the tetramer tied to excited trimer, you mean, huh?
Yeah, in order to sort of rule out that what you're seeing is just non-universal. If you do it this way and choose this parameter, I think you would have to look at excited tetramers and trimers.
Let me to discuss on that. Yeah, for sure. Okay. Yeah. Here.
Yeah.
So if I decrease mu4 over mu3, I see numerically that for mu4 over mu3, about 0.2 B40 over B3 appears. That this is the limit that the ground tetramer appears. At least, I mean, that numerically, yeah.
Because all the states are, I mean, resonant, resonances.